So yeah, I think all this is good. That's the mean calculation, that's fine. Yeah, so this is an interesting point. Like, so when you are running that algorithm iteratively, essentially the loss function which you're trying to minimize, you're not explicitly minimizing this, but essentially what you're trying to do is you're trying to minimize the distance of every sample between every sample to its assigned cluster center, right? So that's what you're trying to minimize. Because if that distance is not minimal, then you can assign that sample to some other cluster center, if that is the minimal one. And that's the whole objective, right? That's how you do the reassignment. And basically, if you think about this, each iteration, you have to compute distance of each sample to all the cluster centers, which means that we'll compute that distance and then we have to perform some kind of sorting. And then you will pick like the shortest distance. And this is exactly showing you that the distance of each sample to the assigned cluster center. Okay? And then you add like all those distances for all the samples. And that's like what the, you can say if you want to say like a loss function or something, which will get minimized. All right, so these are some of the variations, or you can say the parameters you have to choose. The first one is how many cluster centers to use. And that's like, I will say one of the biggest limitation of k-means, because since this is like an unsupervised algorithm, most of the time we don't know how many clusters we have. So that is something which can be estimated. And one simple solution is you can actually try different number of centers and just run that algorithm multiple times. And then you can compute that loss function. And for whichever number the loss function is actually minimal, you can choose that as a solution. Okay. The other issue is when to stop. The demo which we discussed, it was easy because the cluster changer, the cluster center was not changing. So we can stop because there's no point in performing like more iterations, right? There's nothing happening there. Everything is fixed. The other way is you can actually fix the number of iterations. So for example, you have some kind of computation restrictions. So you can limit, okay, we'll only perform 10 iterations or 20 iterations, and then we will stop. And again, like if the cluster centers are not changing, or you can say also like partitions are not changing. For example, the points are not jumping between like different cluster centers. That could be like a good convergence criteria as well. All right, so the initialization, as I said, it plays a very big role, because since it is done it is done randomly. So for example, if you have this kind of initialization, right, second point and third point, there is no way like these cluster centers are actually going to move around to this side. So basically you will just get like a big cluster like this. Okay, and then these 3 points will have to be divided between these two, and most likely I think this will be one cluster center with just 1 point, and these two might be another one, depending upon like how far they are from these cluster centers. So again, you can see like the initialization makes a big difference. Okay, and these are like some of the heuristics which can be used. As I said, you try like multiple starting points, right? And then you can compute like that loss function for whichever try like you are getting the minimum loss function. You just choose that as a result. Okay, so again, randomly picking examples, that was another variation which we discussed. This is interesting. What you can do is you can divide your Euclidean space like into different segments, right? And then make sure that whenever you choose your center, it belongs to one of those segments. So that way you are making sure that at least your centers are actually spread out equally in your data points, within your data points, right? So that's like a good heuristic which can be used sometimes.